Okay, so previously we have been talking about the prime factorization, and then we have presented the fundamental theorem of algebra. We have proved it, and then we have presented some of the consequences of fundamental theorem of algebra. And then now we are going to try some exercises. So exercise 1 is that suppose that n is a positive integer such that p is 2 power n minus 1 is the prime. The first few such primes are 3, 7, 31, and so on. Define n to be 2 power n minus 1 into p. List all the positive integers that divide n. Prove that the sum of all these divisors, including 1 but not n itself, is equal to n. A positive integer that is equal to the sum of all its divisors, including 1 but not itself, is called a perfect number. So we are saying a positive integer is called a perfect number. Write down 4 perfect numbers. Okay, so this is the exercise we need to attempt. So let's try that. Solution. So the positive integer dividing n are integers dividing n, which is 2 power n minus 1 into p, are 1, 2, 2 power 2 up to 2 power n minus 1, comma p, comma p 2p 2 power 2p up to 2 power n minus 1 p. So these are all the divisors of n. Now let d be the sum of these. Okay, including 1 but not n itself. So you can write d as 1 plus 2 plus 2 power 2 plus up to 2 power n minus 1 plus p 2p 2 square p plus 2 power n minus 1 p. Okay. Now by the formula for the sum of geometric series 3.1, proposition 3.1. So by the formula for the sum of geometric series, that is proposition 3.1 we have mentioned in chapter 3, we can write that 1 plus 2 plus 2 square up to 2 power n minus 1 can be written as 2 power n minus 2 power n minus 1. So we can write 1 plus 2 plus 2 square plus 2 power n minus 2 is nothing but 2 power n minus 1 minus 1. Okay, perfect. Then we are actually saying hence d is the sum. D is nothing but 2 power n minus 1 plus p into 2 power n minus 1 minus 1. And this can be written as 2 power n minus 1 plus 2 power n minus 1 p minus p. Now, since p is 2 power n minus 1, it follows that d is nothing but n as required. So the sum of all these divisors is n. Now we need to find 4 perfect numbers. So first 4 primes of the form 2 power n minus 1 or 2 square minus 1, which is 3. 2 cube minus 1 is 7. 2 power 5 minus 1 is 31. 2 power 7 minus 1 is 127. Hence, the perfect numbers, the following are, now these are the prime of the form, but these are not the perfect numbers. So the following are the perfect numbers. They are 2 into 2 square minus 1, and that is 6. 2 square dot 7 is 28. 2 power 4 dot 31 is 496. And 2 power 6 dot 127 is 8128. So these 4 are the perfect numbers: 6, 28, 496, and 8128. Why they are perfect numbers? Because if you add their divisors, the sum will be equal to the number itself. Okay, here we end the question number 1. Now the question number 2 is, so number 2 is that we need to, so let m and n be positive integers. Prove that the nth root of m, or m power 1 over n, is rational if and only if m is an nth power, or you can say can be written as c power n for some integer c. Okay. The right to left implication is easy. We can say the right to left implication this one is easy, as if m is nth power, then clearly m power 1 over n is rational. Okay, because m is a positive integer. Okay, now for this part, for the left to right implication, this part, we suppose m power 1 over n is rational. So m power 1 over n can be written as x over y, where x comma y are integers. Okay, then we can say that x power n is nothing but m into y power n. Perfect. Let p be a prime, and p power a, p power b, p power c be the largest powers of p, be the largest powers of p, which divide x, y, m respectively. Which divide x, y, m respectively. That means p power a divides x, p power b divides y, and that means p power c divides m. Okay. Then the power of p, then the power of p, power of p dividing x power n is nothing but p power a into n, while the power of p dividing, while the power of p dividing m y power n is p power c plus p n. By the fundamental theorem, theorem 11.1, we must have an is c plus bn. Their powers are equal, and hence c is n into a minus b is divisible by n. Now we have shown that the power to which each prime divides m is a multiple of n In other words, the prime factorization of M is the prime factorization of M is nothing but M is equals to P1 and A1 actually, A1 dot PK and AK for AIs to be integers. Hence, M is PA1 product of all these primes power n, and so M is an nth power is required. Okay, perfect. Now we will talk about question number 3. Question number 3 says, which pairs of positive integers m and n have HCF equals to 50 and LCM 1500? So let's solve A first. So we need to find the pairs m and n. So the HCF is actually equals to 2 into 5 square, and the LCM is 2 square, 3, and so this is 50 and 5 cube here, which is 1500. Okay, so the pairs m comma n are 2.5 square comma 2 square dot 3.5 cube. Okay, the first one, which we have written here. The second one could be 2.2.3.5 square, 2.3.5 square, 2 in comma 2 square dot 5 cube, comma 2.5 cube, comma 2 square dot 3.5 square, comma 2.3.5 cube, comma 2 square dot 5 square. Now, these are the pairs, and by looking at the prime factorization of these HCF and LCMs, you can write these kind of pairs. Okay, perfect. Number B is, show that if m and n are positive integers, then the HCF divides the LCM. When does HCF is equal to LCM? So part B. So we need to find out that when HCF divides LCM and when they are equal. So let's try to do that. So HCF of m comma n divides m, right? which divides LCM of m comma n. Hence, HCF of m comma n divides LCM of m comma n they are equal when both when simply you can say m is n. Okay. Now they HCF and LCM are equal when both like HCF of m comma n is n m and its LCM of m comma n is also m, and HCF of m comma n is n, and then LCM of m comma n is also n. So, and this is possible when m is n. Right. Perfect. Part C is show that the m and n are positive integers. Then there are co-prime integers such x comma y, such that x divides m, y divides n, and their product is LCM. So that's again true. So part C is, as we have seen in the proposition 11.2, let m can be m, the prime factorization of m is this one, and n has sk. We define x to be the product of all these. Define x to be the product of all the pi's power ri, for which ri is greater than or equal to si, and y to be the product of all the pj's where power sj, for which rj is less than sj. And a simple example for this one could be that HCF of 2 comma 3 is 1. So comma 2 and 3 are co-primes. Then their product then LCM of 2, 3 is 6. Now this means that when M and N are itself 2 and 3, but you can choose M and N and something like that. So you can say that one of them is M is 4 and N is 15. Then you can say something like that. Yeah. Perfect. Here we will end the exercise part. Then we will start in the next part, the chapter number 12. Thank you so much.